Great. Good morning, everybody. Welcome back to Math 105. Hope the exam went all right for you. I'm going to try and start grading those exams sometime this weekend. Hopefully I will get them all done, but do not be surprised if it takes me until early next week to get all of those graded. Those are a bit more time consuming than single quizzes. Plan for today is we're going to finish our discussion of Standard 6. Laws of logic. We just have kind of two more laws of logic that I would like to talk about today. And then we are going to jump into Standard 7, which is about logical syllogisms, or how to construct logical arguments using sort of the laws of logic that we talked about on Monday and that we'll finish talking about today. As far as office hours go, I don't have any today, but I will have my usual office hours Monday morning and Monday afternoon if you'd like to meet with me. The sign-up for those will go up on Blackboard sometime tomorrow, probably. And as far as homework goes, you may have seen Standard 6 quiz is already up on Blackboard. It will be due on Monday. One comment I'd like to make before we get going for today. Parents' Weekend. For those of you who have parents coming to Parents' Weekend, normally it's a thing where you can have your parents sign up to meet with professors. I'm not going to be going to the Parents' Weekend meetings this year for a variety of reasons. So, if your parents would like to meet with me, I encourage you, or if you think your parents are coming to Parents' Weekend, I encourage you to tell them that I'm not going to be available for in-person meetings. But I also encourage you to get in contact with me, and they can do that through you, if they would like to set up like a Zoom meeting with me. Be happy to talk to them virtually. So, if your parents are coming to Parents' Weekend, I'm not available. If you let me know, I would be happy to set up a meeting with them. Any questions or comments before we get started today? What did the mathematical acorn say when it grew up? When what was once a mathematical acorn grew up, it said, "Gee, on a tree."
Oh.
Okay, so if you recall, last class on Monday, we kind of talked through the three classical laws of logic. I didn't write those down, but those were the law of non-contradiction, the law of excluded middle, and the law of identity. It's kind of all matched up with things that we'd seen before, and we can construct truth tables and show that each of those form tautologies, meaning there are statements that are always true. We also looked at a couple of other mathematical statements and mathematical laws. The law of Modus Ponens, which says that if P implies Q and P is true, then Q has to be true. And the law of Modus Tollens, which said that if P implies Q and Q is false, then P has to be false. Basically saying like similar to Modus Ponens, but using the contrapositive of the statement P implies Q. And what I'm going to do today is to start by talking through two more logical laws that we're going to be using in Standard 7 to help us actually construct, analyze syllogisms and determine whether or not they are valid. So let's start off with transitivity. So this is going to be on the back page of the handout. These two are listed as laws of syllogism. I didn't put the names for the individual laws. I neglected to do that in the packet, so you'll have to write those in for your Standard 6 packet. But the first one is going to be the law of transitivity, which is going to say that if P implies Q and Q implies R, then P implies R. So in other words, if P implies Q and Q implies R, then we know P is going to imply R. Has anyone seen this word before, transitivity, or maybe just transitive, used in a math class? What's the context in which you saw that?
Logic.
Oh, no problem. In logic? Yeah, it shows up a lot in kind of mathematical logic, and we have this property that you've likely seen before called the transitive property that says if A is equal to B and B is equal to C, then A has to be equal to C. It's a property that basically gives you a way to say if A and B are somehow related to each other, and B and C are somehow related to each other, then A and C have to have that same relation through B. Here, when we talk about transitivity, we mean the same idea except we're using implication, where if we have three statements, P, Q, and R, and if statement P implies statement Q, meaning if we have a Venn diagram, our circle for P is going to lie entirely inside, that's supposed to be a Q, our circle for Q, and if Q also implies R, meaning everything inside our circle for Q has to also lie inside the circle for R, then it's going to have to be the case that everything in the circle for P is going to have to lie inside the circle for R. If we wanted to do an aptly example, if the statement P is something along the lines of this apple is red, statement Q is something along the lines of this apple is juicy, and statement R is this apple lacks worms, are arguments that we can make that kind of combines these three statements using transitivity would be something along the lines of if all red apples are juicy, meaning if P implies Q, and if all juicy apples lack worms, this will be our if Q implies R. So if P implies Q, red apple implies juicy apple, and if Q implies R, juicy apples have to lack worms, what would be kind of what could we wrap up this sentence with according to the law of transitivity?
Then red apples lack worms.
Then all red apples lack worms. Then P implies R. I like it. Yeah, that's exactly right. All the apples that are in the red circle have to be in the juicy circle. All the juicy apples have to be in the circle of lacking worm. Oops. This sentence lacked worms at the end. If all the red apples lie inside the circle of juicy apples, if all juicy apples lie inside the circle of worm-lacking apples, then the red apples have to also lie inside that circle. Any questions about what the law of transitivity says? Let's do a quick truth table. So this one is going to be a little bit interesting because we've seen plenty of examples now where we draw truth tables where we sort of start with one or two base statements, whether our base statement is just a P or if it's a P and a Q. But this time, we need to draw a truth table that's going to account for having three base statements that are all maybe unrelated, a P, a Q, and an R. When we just had a P, one base statement, we only needed 2 rows. When we had a P and a Q statement, we needed 4 rows to account for true, 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 false, false, true, and false, false. Now that we have 3 statements, it's going to be even worse. We're going to need 8 rows. And this is why we're not going to do too many examples of truth tables with 3 base statements, because these are big truth tables. The reason why we need 3 rows is because if we want to allow for the possibility of any of these 3 being true and any of these being false, there's 8 different ways that that can happen. One would be they're all true. One would be P and Q are true, but R is false. We'd have a couple for P true and Q false, where R can be either true or false. We'll have 2 for P being false and Q being true, one where R is true, one where R is false. And finally, we'll have 2 rows for where P and Q are both going to be false, namely where R is either true or false. And so basically, if we only had 2 different base statements, a P and a Q, we would have 4 rows, one corresponding to where P and Q are both true, one corresponding to where P and Q, or where P is true and Q is false. We have 2 rows for where P is false, Q is true. Or sorry, we have 1 row for that, and we have 1 row for where P and Q are both false. The problem is, if we add in an extra statement R, we need to double the amount of rows, because if P and Q are both true, we still have 2 possibilities for what R could be. If P is true and Q is false, we have 2 possibilities for what R could be. If P is false and Q is true, we have 2 possibilities for what R could be. And if P is false and Q is false, we have 2 possibilities for what R could be. So we end up needing 8 rows in total. Anyone like to take a stab and guess how many rows would we need if we had 4 base statements?
16.
We would need 16. And then if we had 5, we'd have 32 rows. And I would be really struggling to draw them all on the board. And in general, we're going to have 2 to the n rows if we have n base statements. But here's our basic setup. We have 8 rows accounting for all possibilities of P, Q, and R being true or false. We want to be able to draw a truth column that ultimately holds true if P implies Q and Q implies R together are going to imply that P implies R. So I think it'll be helpful to have columns for each of the individual implications. P implies Q, Q implies R, P implies R. If P and Q are both true, P implies Q is going to be true. If P is true, Q is false, and this column is going to come out to false. If P is false, then no matter what, P implies Q has to be true. Let's see what would happen if Q implies R. I think we're going to start off with true, false, because if Q is true and R is true, Q implies R should be true. If Q is true, R is false, then Q implies R should be false. If Q is false, then Q implies R automatically has to be true. Q true, R true comes out to true. Q true, R false comes out to false. And then the last 2 are both going to be true. Here the truth tables can get very long, which is why this is going to be the only one we really do that has 3 different base statements, because it takes so long to draw. If we want to look at the P implies R column, let's see, if P and R are both true, this is true. If P is true, R is false, this comes out to false. True, false. And then if P is false, all the implications if P involves R have to be true. We can then make a column for P implies Q and Q implies R. I know I'm going a little bit fast, but I don't want to spend like the entire class just constructing this truth table, which we could easily do if we went slowly here. Let's see. So we're doing an and statement involving these two columns. The only way our and statement is true is if both of these columns evaluate to true. So I got a column that looks something like this. Let's see, true, true, false, 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 true, false, true, true. And finally, we can make one last column that'll be for our transitivity statement. Q implies Q, and Q implies R, implies P implies R. Well, we're basically looking, when does the second to last column imply the third to last column? If both the last two columns are true, then the implication is going to be true. If this one is false and that one's false, the implication will be true. False true comes out to true. False false comes out to true. True true is true. False true is true. True true is true. And true true is true. True that. And so in the end, although it took us a ridiculous amount of effort to get there, we have an entire column of truths. And so transitivity law must be a tautology. Because in all 8 possible base cases for whether P, Q, and R are true or false, P implies Q and Q implies R implies P implies R will always come out to true. Mainly because there's no circumstance where this column is true and the P implies R column is false. That would be the only way for the implication to be false, and it never happened. Any questions or comments about that? Bit of a long truth table. I wanted you to see at least one example of a truth table involving 3 base statements, because there are lots of logical laws that involve 3 base statements. This is going to be kind of the only base one that we end up looking at for the purposes of constructing syllogisms in Standard 7. I'm just putting it over here so we have it for later on. But there are logical laws that involve 4 statements, 5 statements. I think I've even seen one before that uses 6 different base statements. And each time that you add a new statement, the amount of rows that you would have, the amount of rows that you would have to have in your truth table will always double. And so if I was feeling particularly vindictive towards you for whatever reason, I could just give you a quiz that says, here, fill in this truth table for a statement with 5 base statements. And it would never end. You would have to fill in, let's see, for 5, that's 32 rows. So we're not going to do. Okay, there's one last law I want to look at before we can say we're done with Standard 6. And that's going to be the law of disjunctive syllogism. Where this law says that P or Q and not P implies Q. Or, if we wanted to write that out in words, we could say, if P or Q is true, and P is false, then Q must be true. So if we wanted to look at a Venn diagram, we can see that if we had two circles for P and Q, this time we don't have an implication, at least not yet, for P and Q. If P or Q is true, that tells us we have to be in one of these two circles, at least. Could be in the overlap. If P or Q is true and P is false, meaning we're in the overlap of this, or we're in at least one of these two circles, but we're not in the P circle, where would we have to be? Yes, in the Q circle. Yeah. Only way to be inside P or Q, but to not be inside of the P circle, is to be inside of the Q circle. And a quick apple example would be something along the lines of, this apple is red or juicy. It is not red. Therefore, what would have to be true? If it's red or juicy, but it ain't red, it's going to have to be juicy. Questions or comments about disjunctive syllogism? Disjunctive syllogism is a fancy name. If you remember, way back in Standard 3, we said that disjunction just means something relating to or statements. Disjunction was our technical name for an or statement. So basically, this is how you can construct an argument using an or statement. And it's written this over here, so we'll have it for Standard 7. Let's see, this is P or Q, and not P implies Q. I don't really feel like drawing a truth table for this one. We've all seen so many truth tables at this point, you're probably sick to death of them. So I'll just say, you can certainly prove this law by constructing a truth table, just like we've done with the others. And this one, you only need 4 rows, because there's only 2 base statements, P and Q. You just need columns for P or Q, not P, P or Q and not P, and then the whole law as a whole. All right, that's going to do it for Standard 6. It's kind of standard where we talk about tautologies, where we talked about contradictions, and where we kind of looked at all of these different logical laws. And now, Standard 7, we're finally ready to start constructing arguments using kind of these different logical laws. Modus Ponens, Modus Tollens, Transitivity, Destructive Syllogism. We're going to be ready now to actually start looking at mathematical statements and see when can we say, oh, this argument makes sense to us, or nah, this argument is complete rubbish. So go ahead and pull out your Standard 7 packet. In the meantime, I'm going to take a quick pause. So I'm going to start by writing something on the second page down, but we are going to come back and look at the first page. I just want to have an example of a syllogism in front of us before we go through and start talking about like the base definitions. If Katie is in the kitchen, then she is cooking. Katie is in the kitchen. Therefore, Katie is cooking. This is going to be our first example of what's called a syllogism, which is basically a 3-line simple mathematical argument. where in general, if you notice, when you look at this statement, it has three basic, this argument, it's made up of three basic statements. The first is this implication, if Katie's in the kitchen, then she's cooking. The second line says Katie is in the kitchen. The third says, therefore, Katie is cooking. Anytime you look at a logical syllogism like this, it's always going to involve three statements. So here I'm back on page 1 for a second. A syllogism is a set of three statements producing a logical argument. Where the first two statements we refer to as the hypothesis. So the hypothesis is made up of two statements, and it's basically, the hypothesis is going to be made up of two statements we are going to assume have to be true. And the last one, the last statement, is going to form the conclusion which may or may not have to be true based on whether the hypothesis is true. But the argument claims it has to be true. Argument claims should be true if the hypothesis is true. So let's take a look at this one. So, according to kind of the definitions, which statement in this syllogism would you say is the conclusion?
Therefore, Katie is cooking.
Therefore, Katie is cooking. So this line here, our last statement, is going to be, I'm going to give myself enough room, the conclusion. And the two statements that come before it are going to form the hypothesis. Whenever we construct a syllogism, we're looking to be able to come up with something that says, in the scenario where both statements in the hypothesis are true, we want it to be the case that the conclusion also has to be true. So if statement 1 is true, and if statement 2 is true, then statement 3, we want to claim, if we're constructing a logical, valid syllogism, has to also be true. So intuitively, what do you all think about this one? If Katie is in the kitchen, then she is cooking. We're assuming that that's going to be true. And Katie is in the kitchen. We're also assuming that has to be true. Therefore, Katie is cooking. In every scenario where both statements of the hypothesis are true, you think the conclusion has to be true?
Yes.
Because of modus ponens. Exactly. So here it can be helpful to, given a syllogism like this, I personally think it's helpful to write it down symbolically, just like kind of we've been doing all semester long. If you have some statements written in words, you could try to write them down symbolically and kind of break it down into smaller pieces. And if we do that here, we can let the statement P refer to Katie is in the kitchen, and the statement Q refer to Katie is cooking. And if we were to write our syllogism symbolically, how could we write this first statement down? We have a P, our P is going to be Katie is in the kitchen. Our Q is going to be Katie is cooking, or she is cooking, if it's clear who you're talking about. How can we write down this first statement symbolically? If Katie is in the kitchen, then she is cooking.
So P with the arrow pointing Q.
Yeah, if P, then Q. P implies Q. So our first statement, we can write in the form P implies Q. Our second statement is just P. Katie is in the kitchen. And so our symbolic argument is of the form, we're assuming that P implies Q and P, and therefore Katie is cooking. So therefore, Q. Dr. Gerstle, what's up with those dots you just drew? If you notice, I wrote dots before the Q. Whenever the dots are just a mathematical symbol that just means therefore. Meaning, what we're really saying when we say this is P implies Q is true, P is true, therefore Q is true. Therefore is just kind of a fancy way of saying the stuff that came before it implies the stuff that came after the therefore symbol. So really, when we write this argument out symbolically without using the therefore symbol, we're really saying the same thing as saying P implies Q is true, and P is true. Therefore, Q has to be true. Is symbolically how we would interpret a syllogism like this. P implies Q, P, therefore Q. This means the same thing as saying the first two pieces both have to be true. So P implies Q and P. If those are both true, then therefore Q has to also be true. Which law of logic does this look like? P implies Q and P implies Q.
Modus Ponens.
Yeah, this is exactly what the law of Modus Ponens looks like. Law of Modus Ponens tells us if P implies Q is true and P is true, then Q has to be true. We constructed a truth table and saw that no matter what your P and your Q are, this statement is a tautology. It's always true in all possible cases, regardless of if P is true and Q is false, or if P and Q are both true, or if P is false and Q is true, or if P and Q are both false. This statement right here always came out true when we constructed the truth table for it back in Standard 6. So what that tells us is this argument, this logical syllogism, is a valid one. So if we were to write that out in words, we could say, this syllogism is logically valid since symbolically since it has to be a tautology. Since it is equivalent to a tautology. Logically valid when we apply it to a syllogism like this is just basically saying, yeah, the conclusion has to be true if the hypothesis is true. That makes sense. If the conclusion must be true if the hypothesis is true. And even though in our hypothesis, we didn't write the hypothesis as an and statement, we just wrote the hypothesis out as two separate statements. If Katie's in the kitchen, then she is cooking. Katie is in the kitchen. Really, you can think of our hypothesis as secretly being a single statement where we kind of used an and statement to combine the two individual statements into one. If Katie is in the kitchen, then she is cooking. Katie is in the kitchen, therefore Katie is cooking. Oops, I forgot to say this is logically valid by Modus Ponens. Really what we're saying is if Katie is in the kitchen, then she is cooking, and Katie is in the kitchen are both true, then it must be true that Katie is cooking. If P implies Q and P are both true, then Q has to be true. This implication is true whether P is, well, I already said this, but P and Q can be both true, both false. One can be true, the other is false. This statement is always true. Mainly saying there's no way for the hypothesis to be true and for the conclusion to be false. If the hypothesis is true, conclusion must also be true. Any questions or comments? This is basically all that standard 7 is doing this sort of thing. Given a logical syllogism like this, we can analyze it, basically go through hypothesis, conclusion. We can write it down symbolically and see if the symbolic way of writing down the syllogism like this, whether or not that's equivalent to one of these logical tautologies, and if so, then our syllogism is logically valid. And if we don't come up with any of these, if we get something, in fact, that's not a tautology, then we do not get a valid argument or a valid syllogism. Let's do one more. Do the second one on the second page. If a pig is dry, then it will roll in the mud. Wilbur the pig is rolling in the mud. Therefore, Wilbur was dry. So here's another syllogism that's written out in words. We have two original statements. These will be our hypothesis. This last one will be our conclusion. And my challenge for you is to take the next 5 minutes, and I want you to try and determine if this is a logical argument or not. Which means I want you to try and write this out symbolically, kind of what we did with this first example. We separated this into a P and a Q, broke it up into the various pieces, and then I want you to try and see, once you get this down symbolically, do we get a tautology or not? It's going to take a few minutes. As always, you are certainly welcome to talk to your neighbors, talk to people sitting around you, and see if you can show whether or not this syllogism comes out to a tautology. just looking at that part. You're not sure how to get started with this one, but feel free to flag me down, or see if you can turn, or you might try turning to your neighbor and seeing if they have same ideas that you do, or any ideas to help you. Now we're being very quiet, which is making me very disconcerted. Let's try and go through this one. So if we wanted to split this up into a kind of a PQ scenario where we write this down symbolically, what would be like a good statement that we could refer to as statement P here?
Biggest drag.
Biggest drag? Yeah, this could be our P is a pig is drag. And what could our statement Q be?
Then it will roll in the mud, or it will roll in the mud.
I was gonna say, yeah, the pig will roll in the mud or something. If we know exactly what we're talking about, that can be our kind of Q. So our first statement in the hypothesis is going to be of the form, if P, then Q. If the pig is dry, then the pig will roll in the mud. Wilbur the pig is rolling in the mud.
True.
That's a Q statement. Can it be a Q statement if the original Q has nothing to say about Wilbur, but this one is referring to Wilbur the pig? So,
The pig is rolling in the mud. Just what the first one.
yeah, the fact that we're referring to a specific pig and giving it a name, Wilbur, doesn't really matter for the purposes of this argument. If I had replaced Wilbur the pig with just the pig, or a pig in general, it's not going to change the argument at all. The fact that I've given the pig a name is kind of irrelevant. So, Wilbur the pig is rolling in the mud. We could just say, we're assuming that statement Q is true. So, our hypothesis is of the form P implies Q and statement Q. How can we refer to the conclusion of this logical syllogism?
Therefore, P.
Therefore, P. Which, if we kind of wrote using our standard language, would be the same as saying, if P implies Q and Q is true, then P has to be true. P implies Q and Q implies P. And my question, this time I'm going to restrict ourselves to this half of the room. I want to get you all involved. Is this a tautology? Or is there a scenario, one or more scenarios, where this could be a false statement?
And this is not a tautology because P can be false and Q be true.
Yeah. If P is false and Q is true, then P still implies Q would check out. Q is true, so that piece checks out, but the conclusion does not check out. So, in other words, what type of statement are you claiming this is if it's not a tautology?
it's a contradiction.
It's never true, no matter what P and Q are?
Well, it could be true, so it could be a contingency.
I think this is going to come out to be a contingency. Because if, let's say, P and Q are true, both true, then this would certainly come out as true. Oops. But if we constructed a little truth table, I think we can see that this is going to give us a contingency. So if we do that really quick, let's see. Let's see, if we do our P and Q columns, we can do a quick P implies Q column, which will be true, false, true, true. Our P implies Q and Q. Let's see, and statement for the last two columns is going to come out to be true, false, true, false. Because if they're both true, then the and is true. If they're both false, the and is false. If they're both true, the and is true. If one's false, the other's true, the and statement is false. And then, if we go to see P implies Q and Q all imply P, well, if this is true and P is true, then it comes out to true. If this is false and P is true, the if statement, the contingency comes out to true. If the and statement is true but P is false, here's where I think we're going to get our possible it's not always true scenario. And if the and statement is false and P is false, then the implication is true. So in other words, what we just found is that our original implication, P and Q imply P, is a contingency. Not a tautology. And since we're looking at a contingency here, something that's not actually a tautology, what is that going to tell us about our original argument? Is our original argument going to be a valid one if it's only sometimes true and not always true? It is not. So, write this down. We can actually go through and say, our original argument is not valid since it comes out to a contingency, not a tautology. In a scenario where P and Q, or where, where P is false and Q is true, the hypothesis is true, but the conclusion is false. So in other words, it's possible for the hypothesis to be false and the conclusion true. And when we construct logical arguments like this, we want to be able to say any time that the hypothesis comes out to true as an and statement, then the conclusion also has to be true. All right, that's going to do it for today. When we come back on Monday, we're going to do a few more examples of looking at syllogisms, because they can get a bit more complicated than this one, these two. And then we will jump into Standard 8. Have a good weekend, everybody.
Thank you.
Okay.
I mean,